Okay, hello, good evening. We'll wait for a couple of more minutes and then we'll start. Okay, then I think we can start now. Uh, Good evening, everyone. My name is Umair Hussain, and I'm a PhD scholar from the Department of Mechanical Engineering, IIT Madras. And I welcome you all again to the doubt session of the Basics of Finite Element Analysis Part 2 course, which is a course under NPTEL initiative. Uh, and this course, as I've told before, this is a continuation to its part one course, which was Basics of Finite Element Analysis. So we studied the basic structure of how we solve an FEM problem in that course, and in this course we are taking up a continuation to that, and we started by discussing the basic logic and algorithm of any FEM problem, and then we extended our discussion to calculate the errors of an FEM solution. So we discussed various sources of FEM error and various methods to evaluate the errors in an FEM solution if we already know the exact solution. So, and we studied about the convergence of those the error convergence of errors in the FEM solution. In last week, we extended the discussion to study the various numerical integration schemes. We started by some simple numerical integration logics such as the trapezoidal rule and Simpson's rule, and then we introduced two mainly used numerical integration schemes in FEM. First one is the Gauss quadrature method, and the second one is the Newton Cotes quadrature method. So we discussed the numerical integration using Gauss quadrature method in last week, and in this week we have continued that discussion. So basically, if we are given some random integration, some random function which is integrates between some limits xa to xb, we can convert that integration to the domain of that integration to the natural coordinate system. So if we are given some domain xa to xb, so we discussed that we can use a mapping function. Suppose here our coordinate system is x. We can have a mapping function and transport this transform this domain to a natural coordinate system zeta. Here the limits of this domain are fixed between -1 to +1, and so we there's a mapping function involved in that which helps us to transform this function into that domain, and plus we the integration limits are also changed from -1 to +1. Then we did this because the Gauss quadration method is defined between these ranges, that is -1 to +1. So if we once we get our integral in this form, integration from -1 to +1, some function, then there's a formula given where we find the functional value at certain points known as the quadrature points and multiply by the respective weights of those quadrature points. So depending on the number of the type of function, suppose it's the order of polynomial we are using, uh, we can choose the number of points we are using. So as many number of quadrature points as we are using, the error would reduce. So the more accurate this method becomes. So this was about Gauss quadrature. Then how do we? Basically, at the end of the day, we are going to use method to solve an FEM problem. So in FEM, we solve for this equation basically. So what are these? These are some sorts of integral statements. So just like we're showing Kij for an element here as an integral of shape function, the derivative of shape functions at I and j node, the ijth node. So if you want to convert this kind of integral into the natural coordinate system, firstly we need to change the derivatives. We earlier we didn't have to deal with derivatives when we were learning about transforming the coordinate system in normal integrals. But right now we have so we can write this Kijes by dx times t psi j e by dx times dx. So, in order to replace this, since we are going to write psi I and psi j in terms of zeta, we need to replace the derivative from dx to d zeta. So we can do one thing. Uh, Look, if we want to write this as d zeta, we multiply by d zeta, dx is already here, right? Similarly, we can do the same thing here. Try d zeta here, d zeta by dx. And of course, this dx, we want to remove and write a, sorry, need to, so we're now going to integrate with respect to d zeta, right? So I need to change this. So we studied that this term here, this is nothing but 1 upon Jacobian of the element. Jacobian is basically dx by d zeta. So that is the derivative of this function, mapping function. So we can write this as, here, and at the end we get a function which is purely written in terms of zeta, and now we can simply apply the Gauss quadrature formula to get the desired integral. So we can see that in this kind of integral, we have three different indexes. First of all, we have ij that varies between the number of interpolation function. So, and this this we studied earlier when we were studying the type of uh, interpolation we are doing. So we give this term this number fm. So this would be the number of approximation functions uh, that are being used to estimate the solution. We remember this term. I want to m psi I ui. So so m represents the number of interpolation function being used to estimate a solution, and then we studied this expression. So this shows an approximation of the geometry. So n represents the number of interpolation function being used to approximate the geometry. So here the number of quadrature points basically determines this. So t represents n here, and ij represents m here. So if we have we consider quadratic type of shape function, suppose, then how do we determine the number of quadrature points being used for an integral? Can someone tell me what is the formula to determine? So basically, we need to find r from the degree of polynomial. What is it? Anyone? What was the formula to find the number of quadrature points from the degree of polynomial? Okay. If someone wants to answer, they can unmute themselves and answer. I'll repeat my question. We have new participant here. So, what is the formula to find the number of quadrature points from the degree of polynomial? Okay, so I tell you, r is equals to p plus 1 by 2. If p plus 1 is odd, then we add a half. We don't deal with decimal. It doesn't make sense. So right. So if we choose quadratic shape functions, then what would be the degree of the integrand for kij? Kij to d psi a by d zeta times d psi j by d zeta times 1 by Jacobian right here. 1 by Jacobian. So since psi and psi j are quadratic, then degree here is 1. Yet also degree equals 1. And what's the degree of Jacobian? Can someone tell me? If we are transforming a linear 1D element to its linear simple natural coordinate system, what would be the degree of Jacobian or 1 upon Jacobian? Okay, so we remember this concept very well. That for a simple linear interpolation, our transformation function here, this transformation function is a linear function, and so it's the Jacobian, that is its derivative, it would be a constant function. And we we found that it is always the size of element divided by 2, h by 2. So its degree is 0. So what would be the total degree of the integrand? Plus 1 plus 2, right? The degree of polynomial p is equals to 2. So, right, we can find r is p plus 1 by 2 is 3 by 2 plus half. It makes 2. So, uh, the number of quadrature points required is 2. So basically the value of n is 2. However, m is equals to the number of nodes plus 1. So m is basically equals to 3 here. We are using 2. So if we use n equals to 2, two quadrature points here, we will get the exact solution. But this won't be, the case does not become isoperimetric. It would become what? Can someone tell me? If we use n equals to 2 here, what would the case called? What type of approximation? Okay, so this is known as subparameter. So to make the case isoparametric, isoparametric means we have same number of interpolation function to approximate the geometry as we are using to approximate the solution. So to make the case isoparametric, we can choose r equal to 3 cost points, but we'll still get an exact solution here, but we are still getting an exact solution for r equals to 2. So we did study some features of Gauss quadrature point. So in Gauss quadrature rule, the quadrature points are not evenly spaced. It's not necessary they're evenly spaced. So, however, they are aligned symmetrically by the center point of the domain. You will observe that in that points table. Uh, and yeah, so got the quadrature points may not be same as the nodes in the isoparametric formulation. So suppose if we uh, have a domain here. So our nodes is, suppose we have simple linear approximation, we use two nodes. So these are the two nodes. However, if we see uh, if we'll choose two quadrature points, they lie somewhere, I think here, Q1, Q2. So right, they won't be same, and of course the Gauss quadrature rule is applied only in the integration limit of -1 to +1. So this was all about the Gauss quadrature rule. Now we move on to the next type of integrations, numerical integration scheme that we introduced earlier. That is the Newton-Cotes quadrature. This is yet another type of integration, numerical integration scheme that is popular in FEM, but not as popular as the Gauss quadrature. It is by far the most used one. So in Newton-Cotes quadrature, we don't need to change the integration limits. We can work between any given limit, and so the formula is given here: xb minus xa multiplied by the value of function at the quadrature point multiplied by the weight. This part is same as we had in Gauss quadrature. We have this additional term here, and right. So this is so the first most important feature in the Newton-Cotes rule is that the domain is still the same. We don't change from the given coordinate system to the natural coordinate system. We'll keep on using this given domain. And the number of quadrature points are evenly spaced, unlike Gauss quadrature. So we are given this domain. So if we want to use only 1 point, I think we can. If you want to use only 2 point, our 2 point would be same as nodes Q1, Q2. If you want to add another third point, we'll have to. So the third point, second point would be to here, the center. Q3 would be here, and likewise we can add more points. So yeah, right. If we no matter how many number of points we take, our first and last would always coincide with the first and last node of the element. So this is the table for the weights and the for each value of r, the number of points we are taking. Okay, so if R is even, we get exact solution for polynomial of degree R plus 1. And if it is odd, we get exact solution for P equals to R. So that is all about Newton codes. So there's not basically much. And with this, we finish the numerical integration schemes. And the next thing for in the course syllabus is the 2D finite element analysis. So in 2D FEM, we basically deal with there are two types, two different classification. This type of classification we already had in 1D FEM. So we had boundary value problems, initial value problems, and the eigenvalue problems. We did this thing in the part one of this course. And in 2D FEM, we also have another classification. So first we have the single variable problems. So here we have uh, uh, we in single variable problems we saw there's only one degree of freedom per node, and but in multivariable problems we can have multiple degree of freedom. I think this can also be done in 1D FEM. If you think about it, we have coupled problems in 1D also. Doesn't matter. So, starting with single variable problem, we have a basic type of very common type of differential equation, which is known as the Poisson equation, which is given by this. So, this type of problem can be used to solve different type of problem. So, mainly one popular type is we use this is used to solve a steady state heat conduction problem, and there are the other type of problems also. Next, any single variable 2D differential equation can be generalized using this equation. This equation. Okay. So here, all the A1, A2, A11, A12, all these values are known functions of x and y, and u is a unknown variable, which is a function of x, y. So u now varies in the 2D plane, xy plane. So this is what we are going to find. And if we make a special case of this generalized equation and put a1 to a21 a00 equals to 0, and a11 and a22 as same value, we get our the generalized equation is reduced to the Poisson's equation again. So that is how a basic 2D problem looks like. And now we have another challenge in 2D FEM is the domain, the geometry of domain. So in 2D, the geometry can get really complicated. In 1D, we didn't have such problem. We had simple line. We could just break it into different elements. That was all. Just transform this each element to its natural coordinate system, -1 to +1. That was all. Even the Jacobian transformation function all was very simple to get. But in 2D FEM, it's not so trivial. So we'll see. First, the in the we know the general procedure of an FEM problem. We discretize the domain to elements, form a weak form. We get the weak form of the given differential equation. So can someone tell me what is a weak form? Just for a quick revision. We did this a long time ago. So you can unmute yourself and answer. I hope there's no restriction for unmuting. So basically, weak form is where we weaken the differentiability requirement of the solution. So suppose if we have a second order differential equation, the weak form would only have first order derivative terms. So that makes it easier to for us to choose the uh, interpolation function for the solution. So that way we don't have to choose higher order polynomials. So that's a weak form, and then we represent the primary variable in terms of approximation functions, which is done by like this. And we apply these terms, this approximation into the weak form, and integrate those terms and get the linear equations. And first this is done for each element at element level, and then later these all these element level equations are assembled into a global system of equations, and we just apply the boundary condition and solve those system of equations to find the prime the unknown variable u. Sorry. So right, so this is the basic procedure of FEM. We have done this a lot of times now. So first thing is the discretization part. So in 1D FEM, it was not an issue as I told earlier. We had just a line, we could break it into multiple smaller lines. But in discretizing 2D geometry, there are numerous ways we can break that. So breaking a line, we get multiple lines, but breaking some 2D geometry, we can have all different types of shapes or different type of polygons. So shape do we use? So there are two common topologies. Firstly, we can break it into different triangles. So we can have like this. So that's how we can discretize it. Uh, so you see, there's some gap left at the outer boundary. So can someone tell me what kind of error is this called when we are approximating the geometry by these known shapes? So this is known as error due to geometric approximation. Alright, so yeah, that's how we can do it using triangular elements. And even in triangular elements, the type of approximation can be linear, quadratic, depending on the number of nodes we can have. So if we choose triangle like this, we can have simple three-noded triangular elements that would give linear approximation. If we increase this to 4, 5, 6, 7, we have quadratic approximation. And we have some different type of elements with uh, even 5 or 6 nodes also. That we'll study later in detail. And then if you want to approximate this using We can also, the other type of topology is using quadrilaterals. So we can, so that's how we can do it using simple quadrilaterals. So again, like a triangular element in simple quadrilateral, we can have linear approximation. We have just 4 nodes around, or if you want to have quadratic approximation, we can have 8, 7, 8 nodes or even 9 nodes at the center. That's how we can approximate using triangular elements as well as quadrilateral elements. So while we are doing this type of discretization in 2D domain, there's something we need to take care of. Firstly, we need to discretize in such a way that we can reduce maximum error. So, depending on the type of geometry, we have to use such type of elements that would it would reduce this error due to geometric approximation. Uh, Also, second thing is element size should be small in areas of high gradient. So suppose that this thing should also be taken care in 1D also. It's not a specific case for 2D or 3D. Suppose if we have simple align element here and we have some solution varying here and suddenly jumping to this value here. So in this area there are high gradients. So in order to uh, uh, capture this transformation of this function or this uh, sudden change in this function. If we have smaller elements in this region, we can capture this type of evaluation of this type of we can say evolution of this function in a better way, more accurately. Also, this transition from low density element area to high density element area should also be gradual. Otherwise, sudden jumps will have will get some errors. And also, if we're using different type of elements in a jump in our domain, suppose we have a 8 noded element here, and here we're shifting to 4 noded element. This causes a problem. This extra node here causes a problem this side. So if we have such type of transition, we have special type of shape functions for that with some different unusual number of nodes, not specifically 4 or 8. Also, other thing we can do is we can just replace this quadrilateral with 3 triangles. That can also solve our issue. So such cases can be dealt using this. So I think that was all about the discretization, and that is uh, till this week we could cover till this point, this topic here. So we are done with this discussion of this week's course content. If there's any doubt, we can discuss it now. Next we can then move on to that problem discussion session. So if there's any doubt, we can wait for some time and resolve those. Excuse me for a minute. Yes, you can ask any doubt now if you want. Okay, if there are no doubts, then we can move forward and discuss some problems related to the content of this week. Okay, so numerically integrate numerically calculate the integral this 0 to pi sin x dx using Gauss quadrature rule. So we did this type of problem earlier also last week using trapezoidal and Simpson rule. Now we'll try how we can do it with Gauss quadrature rule. So since it's not a polynomial we have right now, we there's no way to choose uh, the value of r. So we'll see if the solution is converging and the error is reducing or not as we increase the value of r. First of all, we can start by calculating this integral using the normal analytical method. So sin x is minus cos x so cos pi is -1 and minus cos 0 is 1, so we get 2. So in order to calculate this integral using Gauss quadrature, what is the first thing we need to do? Can someone answer this? How do we proceed use, to solve using Gauss quadrature rule? Okay, so to solve using Gauss quadrature, firstly we need to change the integral limits from -1 to 1. Sin x should now be a function of zeta j times d zeta. So how do you find this transformation function x zeta and this Jacobian f? We have x equals 0 and x equals to pi. We're going to change it to zeta equals to -1 to zeta equals to +1. So we want to have a linear transformation equal d zeta. So now we substitute the value at each node. So at first node we have x equals to 0. Zeta is -1. And at second node we have pi and zeta is +1. So if we add these two equations, we get pi equals 2a, means a equals pi by 2, and b equals to a, I guess. Yeah, b is also equals to pi by 2. So we get transformation function as pi by 2 plus pi by cos pi by 2 1 plus theta. Fine. And what is the Jacobian? So dx by d zeta gives us pi by 2. And we know that this Jacobian is always equal to He by 2, the size of element divided by 2. So now we want to perform this integration here. So first we'll perform it using r equals 0, 1, sorry. So what was the, so r equals to 1, what is the value of our integration point? X equals to 0, and value of weight is 2. So we have our function I'll change it. Our integration becomes minus 1 to plus 1. Sine of x theta is pi by 2 1 plus zeta, and Jacobian is again pi by 2 t zeta. So this is our function here. So we multiply the weight 2 with the value of function at x equals 0. Sine pi by 2 times 1 plus 0. Right. So what do we get here? 2 cancels. Pi times sine of pi by 2. Sine of pi by 2 is 1. So we get pi. It's roughly up around 3.14. So we got the this integral value for one quadrature point. So we can see we have some error here. The exact value is supposed to be 2. We're getting 3.14. So we can try it again using r equals to 2. So for r equals to 2, what are the integration points? Can someone tell me? I really don't remember this. It was plus minus 0.557 something, and weight was 1. Can someone verify if this is right? Have to check. Yeah, not exactly correct. 0.5773. Okay, so we have 1 times value of function at 1.5773 plus 0.5773 plus weight function, weight 1 multiplied by the value function at minus 0.577. So to avoid wasting time, I'll just use my calculator for this. Sine pi by 2 multiplied by 1.573 pi by 2 times 0.043. So pi by 2 is common list. Then we have sine pi by 2 times 1 minus 0.57. That is 0.0116. So we observe, so we're getting something 0.0857. Okay, I'll just recheck my calculation. We have pi by 2 times sine of pi by 2 into 1.5773 plus sine of pi by 2 into 1 minus 0.5773, indicating 0.0857, 0.086. Okay, so we still have some error here. You can give it a try with I equals to r equals to 3 again. Out of space here, I will do it. So for r equals 3, weights are 0 and 0.774. Sorry, the quadrature forms. And weights are 0.888. Okay, so we have a long expression now. I'll just quickly use my calculator for this. Okay, pi by 2 times 0.555 times sine of pi by 2 into 1 plus 0.774 plus 0.888 times sine of pi by 2 is just 1 plus 0.555 sine of pi by 2 to 1 minus 0.77. Let's take pi by 2 times 0.555 times sine of pi by 2 1 plus 0.774 plus 0.888 and pi by 2 is 1 plus 0.555 into sine pi by 2 times 1 minus 0.774. Okay, so we are getting a value of 1.4428. So if we check the error for r equals to 1, we had error of 1.14 minus 2 is 1.14. Then for r equals to 2, we had error of 0.086 minus 2. So we have minus 1.9. Then for r equals to 3, we have error of 1.442 minus 2. 0.55. So error finally reduced at r equals to 3. Okay, so that's how accurate we can get for non-polynomial cases using Gauss quadrature. So I hope this problem was clear to all. If there are any doubts, you can ask me now. Else we can move on to the next question. So now we have 3 different domains. And we have to transform all these to our natural coordinate system. So we simply assume a simple transformation function. Substitute the value at the nodes and get the value. So at x equals to 1 for first case, we have zeta equals to minus 1. and for x equals to 2 we have theta equals to plus 1. So this gives us c equals to 2a means a equals to 3 by 2 and b equals to 3 by 2 minus 1, that gives us 1 by 2. So for first case we have x equals to 3 plus theta by 2. We take the Jacobian, we get half. So again for second case we have x equals to we have theta equals to minus 1. For x equals to 4 we have theta equals to plus 1. We get the equation, we get a equals to 7 by 2. We get b equals to 7 by 2 minus 3. That is half. So again, substitute the value, we get x equals to 7 plus zeta by 2. We take the Jacobian, we get half. The next case we have x equals to 7, we have zeta equals to minus 1. At x equals to 8, we have zeta equals to plus 1. So this gives us a equals to 7 plus 8 is 15 by 2. And b is again equals to half. So we get our mapping function as 15 plus zeta by 2 and our Jacobian is again equals to half. So we observe that in each of these cases we get Jacobian equals to half. So this confirms the concept that we studied earlier, that for simple linear transformations here our Jacobian is always equals to size of element divided by 2. So in each of these cases our size of element is always equals to 1. Okay, so this is a concept that we can verify through this problem. I hope there is no doubt in this. Okay, so if there are no doubts, we can move forward to the next question. So if we're given quadratic shape functions and we have these integral functions for the uh, k, m, and f matrices and vector. So we need to find the integration point for each of these integral expressions. So for the first case, we have all these ax, bx, cx is constant. So we'll start with the case 1. Ax equals to bx equals to cx equals to constant. So now our and we are given that psi and psi j are coordination function, right? So k is equals to x times p psi I by dx d psi j by dx, right? So degree of this is 0. What will be the degree of this d psi I by dx is? So we the psi is quadratic and its derivative would be linear. Degree is 1, and was this also degree is equals to 1. So net degree would be p equals to 2. So we can find r here, 2p plus 1 by 2 plus half. So we get 2. We need 2 cost points, 2 quadrature points to accurately find this integration value. Then we have m equals to so this again is a constant function, degree is 0. Psi I and psi j are given to be quadratic, degree is 2. So this gives us so the net degree of the integrand polynomial is 2 plus 2 is 4. So we can find the number of quadrature points required to accurately calculate this integral. P plus 1 divided by 2 plus half. We have 5 by 2 and half is 6 by 2, that is 3. So to find this integration we need 3 quadrature points. So again f is cx times psi I. Cx is a constant, degree is 0. Psi I is quadratic, degree is 2. So we get the net degree of polynomial of the integrand is 2. So r is again 2 plus 1 by 2 plus half is 2. So we need since the order of polynomial or degree of polynomial is more for m mass matrix, we need more number of quadrature points. So if we are solving a simple an FEM problem, we don't generally take a different number of quadrature point for different integral function. We just choose a same. We make a same choice for all. So that is generally done by choosing the higher number of quadrature points. So out of these 3, we have the max number of quadrature point is 3. We'll just choose this for the current FEM problem and go ahead. So suppose if our constant in the next case we have case 2 we have a, b and c are linear functions. So for case 2 this changes to 1. So now we have p equals to 3. So r is equals to 3 plus 1 by 2. This is again equal to 2. And This changes to degree equals to 1 again. So our P changes to 5 here. So R is now 5 plus 1 by 2. So again it's 3. And for this F, now this degree is again 1. P equals to 3. So R is now 3 plus 1 by 2, again 2. So increasing the integrand by 1 degree, it didn't change the number of integration point uh, till the degree was even, right? If we'll increase the degree by 1 more, now it will change. Now the number of integration point would be 1 more than what we got in these two cases, right? So I hope this was clear. If there's any doubt, you can ask now. Okay, so we can move on to the next problem. So we have to consider same problem as previous, and so we given ax equals to bx equals to x equals to 1, and we have to calculate these integer values for I equals to 1 and j equals to 2. So now we have an element ranging from 1 to 2. So first of all, we need this value of shape functions. For quadratic case, how many shape functions do we have? 3, right? So as far as I remember, was it was something like that. You have to check the first and third. So what was the formula for this? So for first it would be zeta minus zeta 2 times zeta minus zeta 3 upon zeta 1 minus zeta 2 zeta 1 minus zeta 3. So zeta zeta 2 is 0 and zeta 3 is 1. And zeta 1 minus zeta 0, zeta minus zeta 1 is minus 1. So we have minus 1 minus 0 times zeta 1 is minus 1 and zeta 3 is 1. we get minus 2 times minus 1. Zeta by 2, zeta plus 1. So we won't want our minus sign. Again for psi 3, we have zeta minus zeta 1 times zeta minus zeta 2 upon zeta 3 minus zeta 1 times zeta 3 minus zeta 2. Someone remembers the shape function, you can tell me. Zeta minus zeta 1 is minus 1, so it becomes plus 1, and zeta minus zeta 2 is zeta. Excuse me. Zeta 3 is 1 and zeta 1 minus 1, so it becomes 2, and zeta 3 is 1. I made a mistake here. This is minus zeta minus zeta 3 minus 1. So this is actually minus 1. Zeta by 2, zeta minus 1. And so I'll check it again. Zeta 1 is zeta 1 is zeta plus 1. Zeta minus zeta 2 is zeta. Zeta 3 minus zeta 1 is 1 minus minus 1 is 2. Zeta 3 is 1. Again 0 minus 0. We get zeta by 2, zeta plus 1. Right? So yeah, shape function 3 is right. 1 I had to change. 2 is I'm pretty sure this is the one. Okay, so we have the shape functions now. To find k, kij is so element is from 1 to 2. Here a is 1. We have psi prime psi j prime dx. So first thing we need to transform the limit to minus 1 plus 1 and psi prime function of zeta now. 1 upon Jacobian times d zeta. So Jacobian is basically he by 2 and he is 1. So 1 Jacobian is half. So 1 by Jacobian is 2. So we need to find it I equals to 1 and j equals to 2. K 1 2 basically. D psi 1 by d zeta times d psi 2 by d zeta to 2 d zeta. So d psi 1 by d zeta is zeta square by 2. Let's calculate it here. Is 2 zeta by 2 is zeta minus half zeta by 2, and derivative of d psi 2 by d zeta. That is simple, 2 zeta. So Fk12 is 2 plus 1 zeta minus half times 2 zeta times 2 d zeta. Okay, 4 zeta square minus 2 zeta. Okay, fine. So how many integration points we need? We just calculate. It is 2. 2 plus 1 by half, 3 by 2 plus half, 2. So this is equals to, so for 2 quadrature points, the weights are 1 times. So what is our first point? 577, right? So R equals to 2 here, 0.5773. Okay, so these two terms would cancel out. This plus is minus. So what we are left with is 8 times 0.5773 square. So we get the value 2.666. So that would be the value of this integral here. If anyone is getting any other value, please let me know. I'll check. You can even try to calculate this integration value using 3 quadrilateral points. You'll get approximately similar value. I think same value. Okay, so I hope that question was clear. We can move on to the next part now. So we have to calculate the mass matrix using the quadratic approximation function. So we know the mass matrix So if we consider same limit as before, 1 to 2, psi I psi j dx, then our quadratic, we have zeta by 2 zeta minus 1, psi 2 is zeta square minus 1, psi 3 is zeta by 2 zeta plus 1. And if we change our limit from minus 1 to plus 1, we get psi I psi j j times dx, sorry d zeta. And our Jacobian here is 1 by 2. So we can start with M11. We just remove this half, we can consider this later, be same for all. So that is zeta by 2 zeta minus 1 times square is. So we need how many uh, quadrature points? 2 plus 2 is 1. Sorry, 2 plus 2 is 4. So 4 plus 1 by 2 is 3. 4 plus 1 by 2 is 5 by 2 plus half is 3. We need 3 quadrature points. So we have 0.555 times. So what is our, for r equals to 3? We have 0 and points plus minus 0.774. Then we have 0.888. We'll start with plus times, then zeta equals to 0. So I think this function becomes 0 automatically. It's basically 0, 2, 0 by 2 multiplied by 0 minus 1. So the whole thing becomes 0. Then we have again 0.555 times function minus 0.774 by 2. Minus 0.774 by 2 times minus 0.771 whole square. So we have So we have 0.555 times 0.774 by 2 into 0.774 minus 1. This whole term is squared. So we get a small number 3.042, and this next term is 0 already. Then we have 0.555 times minus 0.774 by 2, and here we have minus 0.774 minus 1, and this whole term is squared. Here we get 0.2616. So we add to this 0.0042, get 0.2657. So I think the idea is pretty clear. So likewise, we can choose different shape functions and find the mass matrix. So to be half or h by 2 times some 3 by 3 matrix. Obviously, the first element would be 2657. I hope this picture is clear to you all. I don't want to make it too long and boring. So, if there is any doubt, you're free to ask now. Yes, we'll move on to the next topic. Okay, so again we have some integral value from minus 1 to plus 1 to the power 5 minus 6x square plus y. So we need to solve this using Newton-Cotes rule. So we can just start with simple r equals to 2. So our integration domain varies from equals to minus 1 to plus 1. So that so x equals to minus 1 and x equals to plus 1 would be our integration points. So what was the formula for Newton-Cotes rule? It was x b minus x a, right, times weight 1 times value of function at x1 plus weight 2 times the function at x2. I think weights for 2 points, so what was it, half or 1? To check. Can someone tell me? Yeah, for 2 points it's half. It's b minus x. Okay, so here xp minus xa becomes 1 plus 1 and half of value of function at minus 1. So minus 1 to the power 5 minus 6 into minus 1 square plus 5. Again we have half of the value of function as plus 1. 1 to the power 5 minus 6 1 square plus 5. So we get 2 times uh, half of 1 to the power 5 is minus 1, minus 1 to the power 5 is minus 1, and minus 1 minus 6 plus 1. So we have plus 5. So that gives us minus 2. Minus 1, minus 7, minus 2. Okay. Then we have half of, here we have 1 to the power 5 is 1, minus 6 plus 5. So 1 plus 5 is 6, minus 6 is 0. So we have here, so we get minus 2 as the integral value. Just check the exact solution very quickly with the calculator. Minus, so it's x to the power 5 minus 6 x square plus 5 integrate from minus 1 to plus 1. So actually it's supposed to be 6, so we're getting huge error. So we can try do one thing also. You can check it using Gauss quadrature rule. So if we have r equals to 2 there, since the integral limit is already between minus 1 to plus 1, what we have is weight is 1. The value of function is for cos points are plus minus 0.5773, right? Yeah. So we have minus 0.5773 to the power 5, 6 into minus 0.577 to the power 2 plus 5 0.5773 to the power 5 minus 6 into 0.5773 square plus 5. So these two terms would cancel out. One would be with negative sign, other would be with positive sign. Then we have minus 12 into 0.5773 square plus 10. Quickly calculated using my calculator. So my initial type 0.5773 square plus 10 gives us 6. 6.0006. So actual value of this integral using analytical method was also supposed to be 6. So we see for 2 points our Gauss quadrature formula is giving us pretty accurate value compared to this, compared to the Newton-Cotes rule. So I hope this problem was also clear. Otherwise we can move on to the next problem. So again, in the next problem we have an integral minus 1 to 1 e to the power x squared dx. So again we will use the Newton-Cotes rule for r equals to 1, 2 and 3. So for r equals to 1, so this becomes, so we just have one weight, so it will be 1, and we just have 1 point, so we'll take the midpoint. So our function is e(x to the power 0 square. So it gives 2 into e to the power 0 is 1. Get 2 for r equals to 1. Right, so if we take r equals to 2, then we have, so we have 2 times half of, so if you have 2 points, so 1 point would be minus 1 square, another point would be plus 1 square. Again we have 2 into half of e to the power 1 square is e, half of e plus half of e is e. So we have 2e now. Let's calculate the exact value. 2 is 5.436. For r equals to 3, we have 2 times. So for 3 we have the weight distribution as 1 by 6, 4 by 6 and 1 by 6, right? Yeah, 1 by 6, 4 by 6 and 2 by 6. 1 by 6 e to the power minus 1 square plus 4 by 6 e to the power 0 plus, sorry, 4 by 6. Then again we have 1 by 6 e to the power 1 square. So we get 2 into e by 6. Then we have 4 by 6. We have again e by 6. 2 times e by 3 plus 2 by 3. That gives us times e by 3 plus 2 by 3 times 2 by 3. That gives us 3.145. Okay, so I think we have converted to some value. Let me check the exact value of this integral in my calculator. E raised to the power x square integrate from minus 1 to plus 1. Okay, so the exact value is 2.92. I think we are approaching that value as we are increasing R. So I hope this was clear till here. Now we can take a problem that was given in assignment. I think it was an interesting problem. So we had to find this integral using 3-point Gauss quadrature rule. So we have integral from 0.1 to 1.3, 5x e to the power minus 2x. Okay. So first of all, we need to transform this integration limit to the natural coordinate system limit. So we have x equals to a plus b zeta. So at x equals to 0.1, we have zeta equals to minus 1. X equals to 1.3, we have zeta equals to plus 1. We add it, we get y equals to a equals to 0.7. Yeah, and we get b equals to 0.7 minus 0.6. So, and the value of Jacobian is 0.6, right? He by 2. So we have a transformation function x equals to 0.7 plus 0.6 zeta, and the Jacobian is, so we transform this integration limit -1 to +1, we have 5 into 0.7 plus 0.6 zeta to the power minus 0.7 plus 0.6 zeta, and this thing is multiplied by Jacobian times d zeta. So I is 5 into 0.6 is 3. 3 times 0.7 plus 0.6 zeta e to the power minus 2 0.76 zeta. If you want to use 3 point, then we have 0.555 times this function evaluated at minus 0. Was 7 something. Let me check. 0.774 plus minus 0.774. Plus 0.888 times f at 0 plus 0.555 times f at 0.774. So I'll just use my calculator for this. And if you can get the answer, you're welcome. First, calculating f at minus 0.774. So 3 into 7 plus 0.6 times 0 minus 0.774, and this thing is multiplied by e to the power minus 2 times 0.7 plus 0.6 6 into theta value minus 0.774 0.774. So we have 3 times 0.7 plus 0.6 times minus 0.774. This whole thing multiplied by e to the power minus 2 times, so 0.7 plus 0.6 into minus 0.774. So we get it times 12.2396. Then we calculate the same thing at plus 0.774. Just remove the negative sign. We get 2.1814. And now the function value at f equals 0 at place the value as 0. Five point 1785. So this gives us 0.555 times 12.2396 plus 2.1814 plus 0.888 times 5.1785 is this 12.6021. Just to verify, we'll also try to solve this using calculator. The exact value 5 times x times e to the power minus 2 times x. The integration limit is 0.1 to 1.3. 1.35x to e to the power minus 2x. Okay, the actual value is quite off. It should be exactly equal to 0.8938. Okay, never mind. So that is the value we are getting now. I hope I didn't make any mistake here. If there's any, please let me know. And if there's any doubt, you're free to ask now. Yes, we'll quickly move to the next problem. I think we are out of time, but we can just cover one simple 2D weak form calculation problem. So we need to find the weak form of this function here. So if we want to find a weak form, we first write the weighted residual statement. Gradient minus of x square plus y square. So this is the weighted residual statement, and we just wherever we have the second order derivative term, we just do the integration by parts. And so here we have this term here. So minus w time minus So we have this first term here, we apply integration by parts, and so we just move the derivative, and then we are done. And we get a boundary integral term, and this term is exactly the same. So we are left with W times V time gradient T d omega equals to W times x square plus y square, and then we have our boundary term. So this is how we get a weak form in 2D problems. So if there's any doubt, you can ask now. Otherwise, we can stop the session here. Okay, so if there are no doubts, then we can conclude the session here. I thank you all to join the session, and we'll continue our discussion for week 5, the next doubt session on the same day, same time, Tuesday, 7 p.m. I hope to see you all again there. Thank you for your patience. I will conclude the session and end this meeting now. Thank you so much.